Okay, so hopefully you see clearly the screen now. So again, this is about chapter 3, and chapter 3 is on capacitance and capacitors. So what are basically capacitors? So here's a picture of a capacitor. I think I've shown this to you before. So this one is our electrolytic capacitor, the large ones. No? But actually, this is a zoom version of a picture probably, and therefore, no, these are not the actual dimensions of the capacitors. These are kind of small in real life. And then again, another type now, which may be a flat one, and they call this the ceramic capacitor. No? So these are basically in our printed circuit board. A printed circuit board is that layout of plastic now where you see electronic or electrical devices attached to it. No? So you have that in your different circuits of your computer, in your cell phone, no? And many others. We call the plastic where these devices are attached as PCB, the printed circuit board. Now, capacitance again are devices that stores temporarily electric charges. No? So what we will encounter later on are two metal plates or metal conductors. And our first understanding of metals is that they are not able to store charges because if you hold the metal, the charges will eventually transfer to our hand. No? But somehow we can actually store charges in a metal so long as we isolate the metal, we keep it from touching any other objects so that the charges will transfer to that object like the hand. No? So if they are isolated, we can put charges there. No? But somehow the idea is it can only store temporarily charges. So we have here our capacitor. No? The capacity to store charges depends on the potential difference or the voltage. So if you impress upon the capacitor, if you put the capacitor inside two differing or different potentials or electric potentials, then charges there will eventually flow. No? We understand that the flow of the charge is from the lower potential to the higher potential if it's an electron. However, if it's a positive charge, then it will travel from higher to lower potential. No? So whenever the 2 points have two different potentials, then charges eventually travel or flow. No? But somehow in a capacitor, it's going to stop. No? The flow there will stop whenever the capacitor is fully charged. So there's this idea in a capacitor that we can also fully charge the capacitor. Now, if two identical spheres are at different voltage or potential difference, the one with the higher potential stores more charges than the other of lower potential. If the voltage of an object is doubled, then the amount of charge is also doubled. So we will note that Q being the amount of the charge that is maybe present in your capacitor is affected by the potential difference V. They are directly proportional. So higher voltages or higher potential difference means greater or higher charge. No? And of course, the charge there is in coulomb. No? Now, when we make this proportionality equal, then we add a constant here called C. No? And C is what we call the capacitance value in farad. No? So eventually, when we complete our equation, we have Q to be equivalent or equal to C times V. No? So Q is the charge, V is the potential difference, while C here is known as our capacitance. No? Now, in the next slide, we will see the unit that we attach to C. Let me erase this. So our unit for our capacitance is in terms of farad. No? So it is measured in farad. But however, 1 farad is exactly a very big value. And the way we get it from our previous equation, if you transform it, then we will be dividing Q by V. If Q is divided by V, then we have 1 coulomb per volt. And that value, 1 coulomb per volt, is known as 1 farad. No? But again, a farad is a very big quantity. So what we commonly see are only units in micro, which is indicated by this mu symbol, nano, which is maybe letter N. And again, these are small quantities because they're expressed in an exponent, like 10 to the minus 6 for micro, 10 to minus 9 for nano, while 10 to minus 12 for picofarad. No? So these are the common units that we have whenever we encounter the unit of capacitance. Now, again, the way we see our capacitor is that we have a, a parallel plate. And again, this parallel plate is our idea when we of a capacitor. But somehow in our modern circuits today, they don't look exactly like this. So somehow, there's a lot of factors that we see here. And again, for modern day capacitors, they apply the same principles as well. Now, we attach a wiring to our circuit and we realize that one plate will cause electrons to travel and collect it. So if electrons travel to that plate and therefore it will have an excess of electrons, then it's going to be a negative charge plate. So again, because electrons have been abundant, or it gains more electrons. Now, the plate which the electrons left will now be left with a net positive charge. And then therefore this one will become a positive plate. And therefore, once they have varied numbers of electrons, then an electric field now will be set up. So since this is a positive and a negative plate ang sa wala, then an electric potential now will exist, or an electric field now will exist inside the plate. Again, this one will happen whenever we attach a battery here. So our battery again is indicated by this long and short line. So you see a long line here, a vertical long line, and then maybe a short line. And this one now is a symbol of our battery. Now we call this as a schematic symbol. And again, our schematic symbol allows us to draw it in a piece of paper, a circuit. So that's the essence of having some schematic symbol. So we will also introduce a schematic symbol probably for our capacitor later on. But this is now our schematic symbol for a battery. Now, the positive side again is the long line, while the negative side is this shorter line. So this is what we call a direct current battery. Now, our capacitance again can be calculated by dividing Q all over C, all over V. Now, capacitance and capacitors. So we will deal with parallel plate capacitor. We will not talk about the electrolytic capacitor that we just see. However, the functions of our modern day capacitors act the same way. And again, how relevant and how important are these capacitors? They are used in most of our electric motors. In most of our electric motors, like the ones that we see in our water pumps. So water pumps are examples of this. Like our electric fan at home. They all contain some kind of capacitor, and usually the capacitor here may be called as a starting capacitor. Now, the purpose of the starting capacitor is that it makes the motor of the the pump turn on its regular speed. Now, if this capacitor is kind of damaged, like that in an aircon, And usually you know that the capacitor is damaged whenever it is already bulging, kung nagabukol na siya. No? So usually it's kind of flat, no, on one end. However, when it starts to bulge, no, mahabok na siya, then that's one indication that the capacitor is not or is already damaged. No? And when that happens, usually the motor of your aircon will no longer spin. No? So barato lang siya, no? Kung balaan mo nga, mula ng guba, yeah, baklan mo dito, then i-replace. Manda na naman, no? However, no, some of you will bring it to a technician, and even though the technician probably knows nga mula ng guba, no? But since it is there, no, in the technician, then tagaan niya na isang damo nga lista guro sang guba, no? But somehow, amo lang to galing yun kayo yan, no? The capacitor lang, no? And again, no? Because of the many things he opens up and check, no, in your computer, in your aircon, he may bill you, no? Dako ang bill mo, no? But actually, guba lang to gali ang capacitor nga barato man lang, no? Now, the most common type of capacitor, no, is the parallel plate capacitor, and we see it like this, no? So there are two, no, metal plates here. And again, no, these metal plates are probably drawn in or are positioned like this. So these are your two facing plates. And again, no, these plates will eventually have, no, three factors, no, that you can cause to vary its capacitance. Now, one factor according to this, no, that we can cause, no, the change, no, or the increase or decrease of the capacitance is the area. So the first one, no, that we will note down is letter A, the area of the capacitor plates, no. So how wide, no, how wide are these plates affect the degree of the capacitance, no? And another factor, no. So again, no, first there is area of the plates. Next is the distance, no. So how wide is this opening, no? So how spread, no, or how distant are the two plates together. So you may call that as the distance of separation. Okay, so how far or how close you place them together affects also the degree of the capacitance. And another thing is the addition maybe of, so you notice here, no, there is a, so you notice here that there is a gap, no, there's a gap. And since there's a gap there, now what you have there in the gap is basically air, no. Now if you fill this gap, no, instead of air, you place it with some other kinds of insulator, or they call it as dielectrics, no. So butangan nyo na some other than air, the space in between, no, it may also affect the degree of, no, the capacitance value also, no. So again, no, the second one is the distance of separation or the distance between the plates, no. And the third is the presence of a dielectric, no. So three factors that probably, no, influences the plates, no. But somehow this plate will not, no, be charged whenever, no, we do not put a battery. So there's a need for us, no, to always include or connect the capacitor, no, with a battery, no. So again, the long line is the positive side, the short line is the negative side, no. So again, no, the electrons here will eventually, no, travel to the positive side of this plate, no, and then again, no, the negative end will now start to also cause the electrons to go in this direction, and therefore making this a negative plate, no? So again, no, the effect of the capacitance. So if you If you will increase the plate, the area of the plate, it will increase the capacitance. If you will decrease the distance, then you will cause an increase in the capacitance also. And likewise, the addition of a dielectric. No? So factors that probably increases, no, the degree of or capacitance. In a parallel plate capacitor, if the plates are exactly, no, projected or placed very close to each other, no, so kung papalapiton sila kuno, anong matabo, no? So the electric field that is set up, no, is believed to be, no, equally distributed siya all throughout the plates, no, compared nga layo siya, no. So if the plates are relatively farther from each other, then the electric field may probably concentrate on one side lang, no. Hindi siya mag-evenly distributed all throughout, no. So maybe there are some portions of the plate that may have less electric field, and other parts there may have more electric field, no. However, when they are made to move closer, then we can have an even or unequally distributed electric field. Okay, so moving on. So here is our equation again, no? That may probably, no, affect the degree of the capacitance, and we will see here, no, that our initial equation for C is Q over V, but of course your Q and your V, no, can be replaced with this epsilon E sub O or something like E, no? We call it as an epsilon value, and its value is this one, 8.85 times 10 to minus 12, no? So that's the value of the epsilon times the area divided by the distance of separation. Then you could have your value of the capacitance. So that is another way of finding the value of our capacitance. Now here's an example of calculating the charge, no? So if you're given a value of capacitance, so if you have a 20 microfarad capacitor and you place it, no, or put it in between, no, a battery that has a potential difference of 5 volts, then we'll just multiply 20 times 5, no? Or 20 times 10 to minus 6 times 5. No? So you will have eventually 100, no, times 10 to minus 6 coulomb, no? Because this is now a charge. Or that is equivalent to 100 microcoulomb. No? So getting the charge given the capacitance and the voltage. Okay, so moving on, we have, again, we can also connect our capacitors, guys, in some kind of uh, a combination. No? So we could have a picture. So this is our picture of our battery over here. And we can also have, no, a picture of our capacitor. No? So the next one that I'm going to draw here, this is the schematic symbol of no, of a capacitor. No? So usually a capacitor is drawn with two no, parallel plates, and of course we see this already now in our previous diagram. No? So we use this symbol similar to the parallel plate capacitors because the earlier versions of capacitors again are like, no, that of a parallel plate. No? Now another way that they draw this, no, is like this. No? So let me draw that. No? Another way of drawing the capacitor, guys, no, which you may also encounter, is that ang isayaya ka end, no, is kind of curved. No? So it's like a letter C. No? So straight line and then something like a letter C. No? And again, that's another way to draw our capacitor. So schematic symbol for our capacitor, no? Two-way. No? Now here, we see here a combination of, no, parallel connected capacitors. No? Again, we say that these are connected in parallel because if we are going to detach, no, so for example, I decide to detach one of these capacitors. So I have here three actually, no? So from the drawing, I have three capacitors. If I decide to remove one of the capacitor, the entire circuit is not affected, no, with the removal of one capacitor. So I can simply, no, add or remove any capacitor without affecting or cutting, no, the flow of charges in the circuit. Okay, so that's one thing that we see with parallel connection. Now, it's very similar to the connection that we have in our house, in our homes, or in our workplace. No? We can simply add an appliance like an aircon. We can add an electric fan. We can remove it from the circuit without affecting the whole, no, the whole circuitry in your house. Now, if it happens that I'm going to switch off my electric fan and then the whole house, no, will lose its lighting and everything, no, will not work anymore, then that's not parallel connection. No? But you notice that one does not happen in the house. If you decide that you are through using your microwave oven, it never affects the functioning of the lighting, your TV, you know, and other devices. No? And it simply shows that there is no a connection in your house that is simply no parallel connection. We don't connect it in a different fashion. Now, another thing is that in your house as well, if they are all connected in parallel, then the voltages of these devices are all the same. So you'll see that your TV, no, is 220 volts, your electric fan is 220 volts, and all the rest of your equipments are all 220 volts. They share the same voltage. But again, no, when you remove or you are through with one of them, you don't have to, no, you don't have to be worried not to switch them off, no, because they are somehow not connected, separate from each other. No? So again, no, that's one. Those are some characteristics of parallel connection. So the other word for our capacitor, by the way, is that we also call it as condenser before. No? So other devices, and in the future, now we may encounter a different device, and that will be a resistor. No? But that's not our topic today. No? We will reserve the discussion of the resistor, no, sometime in the future. No? Oh, so again, no, parallel connection. So let me erase this. So the the thing that we notice, no, with parallel connection is that the first one that I already pointed out is that the voltages of the source, no. So from the outlet in your house or from the battery, no, that we have, any device that we add here or capacitor that we add, they will all have equal voltages. So the voltage of the source or the battery will be equals to the first voltage of capacitor 1. Capacitor 2 will have the same voltage, no, according to this equation. No? So this is one property, no, of parallel connected, no, resistances. No? So for parallel uh, connected, not resistance but capacitance. No? So the first characteristic that we will notice is that the voltage, no, of the source or the total voltage equals to V1, it's equals to V sub 2, it's equals to V sub 3 if there are only three of them. But if there are more, then you can simply continue adding this. No? Now, another characteristic that we will see here is that once we now connect this to the battery, then it's possible that no, the battery will now provide a charge. No? So from the battery, electrons will now travel, or charges will now travel, no? And they will now start to enter the capacitance. No? So the first charge will go to capacitance number 1. Another charge will go to capacitance number 2. And then another one will go to capacitance number 3. So you'll notice that the total no charge, no, so it's just like water. As water leaves the faucet and or maybe no enters your home, no, it will be split into different pipes because the supply no pipe will have to go to many other portions of your house, like your toilet, your sink, no, lain-lain yung mga portion na may mga nagakinahanglan sa tubig. So the water there will be split into 3 different directions in the case of our drawing here, no. And again, no, let's say we will call the first charge here, no, that enters capacitance 1 as Q sub 1, no. So Q sub 1 is the first amount of charge. Q sub 2 is our second amount of charge. And then Q sub 3 is our third amount of charge, no, that goes to capacitance 3. No? Now, since they are merely a split no, amounts of charges, and they all come from the battery. No? So again, no, our battery provides the total charge. No? However, these different charges are split into 3 different directions. No? So you have here Q1, you have here Q sub 2, and finally you have your Q sub 3 over there. No? And again, these 3 values of charge, no, when you add all of them, no, add Q1 plus Q sub 2 plus Q sub 3, they will simply add up to the supply charge. No? So ang ining tatlo naman, no, they will start to pass the capacitance and eventually no, converge again. Dili naman sa dalo, matipo naman sila. And again, these charges will now go back to the battery no, as Q sub T lang gyapon. So again, no, the charges are simply added. So this is our second no, relationship. No? So for parallel connected capacitance, our next principle here is that no, our total charge is equivalent to the sum of the individual charge. No? So, though parehas lang sa pipe again, no, our idea there is similar to a pipe which carries water and eventually no, distributes it to several smaller pipes. So therefore, na ang tubig na tunga-tunga lang siya. Na? Okay, so that's the second principle. No? And then therefore, our next idea there is that if Q happens to be equivalent to C times V, no? So that's our basic equation. No? Then therefore, no, if our Q sub T is equals to, no? So if Q sub T is equals to some total capacitance multiplied by total voltage, no? So if QT is equals to C sub T times V sub T, and if Q1 is equals to C sub 1 no, times V sub 1, and then plus no, C sub 2, V sub 2, no, plus C sub 3, V sub 3. No? So again, no, ang initialin ng equation. Again, this equation no, comes from no, our idea of total charge equals Q1, Q2, and Q sub 3. No? Now, we will notice that ang aton V nga ini, no, they are all equal no, according to our first principle. No? So if they are all equal in algebra, if a variable no, is simply equal no, and ara lang siya sa kada term, then we can factor them in one form. No? So factorable gali ang V1 being equal to V2 and being equal to V3. We can simply call them as V sub T. No? So if they're factored out no, as V, then you'll see that another V sub T is found on the left side. So if V sub t is found on the left and on the right side, then we can cancel it out, no? Leaving you, no? Yung total capacitance gali, no? The total capacitance is simply, no, the sum of the individual capacitances, no? And I'm going to supposedly write it as principle 3 here, no? So again, no, for number 3, no? The principle, so that's basically, no, C sub t is C1 plus C sub 2 plus C sub 3. Now, if there are more devices that you add, then you simply combine them. No? So again, these are the three principles for parallel connected, no, capacitances. No?